Okay, I think we'll get started. So today we're going to come back to the analog to digital converter. We did do this in Lab 3, but now we've gone through the pulse width modulator and the DAC. Let's get back to the analog conversion. This has a 10-bit analog to digital converter, the 12F1822. We'll need several registers, the AND cell and tris, and then the ADCON 0, the ADCON 1, and then the ADRES high and low. And these are all important banks for using the analog to digital. This really just sets up, say, hey, we're going to turn one of the pins to analog. This is sitting over on bank 2, and the rest of the analog to digital conversion registers are back on bank 1, or on bank, I think I said 2 here, bank 3, and these are on bank 2. These two guys are what sets the pins and the setup for the analog to digital and the initiation of it, and so it kind of takes over automatically, and very little coding actually when we get here. And then this is where the result is stored. And so because this is 10-bit and these are 8-bit controllers, we need actually 2 registers. And you can choose to put 8 bits here and 2 here, or 2 here and 8 here. And we're going to choose to put 8 here and 2 here, the two least significant bits down there. Now what we're going to make here is we're just going to hook this, we're going to use RA0 as the analog input, and we're just going to have a wire dangling there acting as an antenna. And so this will be gathering in some noise, and what it'll do is it'll convert that to a digital signal. And then we will read, we're going to actually read one of the bits in that signal. If we read a very low significant bit, that'll basically be fluctuating completely randomly. And if we use a higher bit, then that will more often than not be off, except for high noise spikes. So what we're going to be able to do is make actually a nice random telegraph process. And if you aren't familiar with a random telegraph process, no worries, it's not something you need to know here, all of the physics and mathematics behind it. But basically what's happening is that you have just a random toggling between 1 and 0. And the amount of time that it stays in one state is random, but it has a correlation or a coherence time. So depending on how we set things, we can have a unlikely to make a transition or more likely to make a transition. So this could be useful for generating a random telegraph process. We're not going to go deep into that. We're just going to kind of see that happening. We're actually going to use this as a proximity detector, so we're going to be able to we act as a pretty good antenna. So certainly if we touch the wire, then the voltage basically swings all the way, and we're going to get pretty much, even if we were to use the highest most significant bit, the highest value, so up around 5 volts, we'd hit that often if we're holding on to it. If we choose an intermediate one though, we can actually get it so that we can be kind of close but not touching the antenna, and that will initiate this random telegraph process. And then finally, what we can do is if we use a more significant bit, then that's almost going to always be off unless we actually touch the wire. So we're going to be able to kind of do 3 very much related things in one here. All right, let's go to the computer and try to work on this. Okay, so I'm going to just demonstrate, and actually I'm going to pause this and put this on the scope as well. Okay, so right now I've got it set as the proximity detector. So we see that we're in the off position here. And as I get close, but not touching, here's our antenna right here. And you can see the scope as a very much, it doesn't stay in its state very long. It's likely to have a transition because when I touch it, we basically are swinging 5 plus or 0 to 5 volts because we are such a good antenna. But we are looking at a lesser significant bit, and we'll talk about exactly what that is here, but you can notice I can get within range and I can just get that going. You can see here that we can have a random telegraph process with a much longer coherence time than if we get really close or touch it in a very short coherence time. Okay, well, let's look at the code now for that. Okay, I'm going to unplug the power and not hot swap this, so I'll make sure all the power is off and put my PIC12F1822, so using a PIC12F1822. Okay, so with this pin, we're using one of the pins that are programming the PIC from the PIC kit. So we have to swap that back and forth between the power supply. Okay, so let's start up MP Lab. So I've got MP Lab up here. We'll start a new project and we'll walk through this. We have done this in earlier labs, but good to do it here now. We haven't done it in a while. So you'll choose a microchip embedded and you'll just hit next. You could use 8-bit. I'm going to just use recently used because we've been using this and that's what we're using. Then it should recognize your PIC kit, whether that's a 5 or a 4 or a 3 or whatever else you're using. So we pick that as our tool, hit next. We don't need this debugger. Then we're going to be doing assembly, so we want to choose the assembler, not the C compiler. So we hit next, and let's call this analog digital conversion random telegraph signal. And we'll finish that. Okay, we can close this. I'm going to, before I forget, I'm going to let me do that a little slower. I'm going to go to settings, then I'm going to go to PIC12F1822, then power, and we'll power this with the PIC kit. So we will power this with the PIC kit, but we won't be able to run it completely because we're, like I say, the R0 pin is also one of the programming pins from the PIC. So hit apply. Okay. Now what we want to do is go to source file, right click, new assembly file, and we'll call that, and this will be our main file. So we'll just type main, and that'll be a main.s file. So now let's go out to my GitHub page, and we will go to our repository, the PIC12F1822, and we'll get the analog to digital. And this is the first one there. So let's grab that, come back to here and paste that in. And let me just build, make sure it's all working, and load. This message will pop up just to protect your PIC or your microcontroller. In this case, PICs can handle 5 volts, so that's good. And looks like everything worked. Okay, so the first part, that's just the configuration bits like we've always been doing. Here's the res vector or reset vector, and so this just tells the program counter where to start. Then we have the main part of the code here, and this all has been the same throughout here. This is just getting our oscillator speed and so on. But here we need our first register, the AND cell, and we are going to set RA0 to analog. So everything else is digital, because RA2 needs to be, we're using that LED as an indicator light there. So there we are, that's analog. Then we go to our tris. We want RA2 to be an output and RA1 to be an input, the analog input. And then we move that to our tris. Now we have ADCON 0. So let's go and look at the data sheet to see what we're actually doing here. So I'm going to pause the video and pull up the data sheet. Okay, got the data sheet up, and as we were told here, starting at 130, page 130, we talk about the analog to digital converter, and I think it's a bit down here. Pretty good information here, kind of nice to read that through, but let's go to ADCON 0. Here we are. So, and then I will try to get these side by side. Okay, so here we are. We've got all zeros. Okay, so let's see what that's telling us. So pin 7, bit 7 is 0, so that could be either 1 or a 0, that doesn't matter. We're going to select the channel, so we're going to use the channel 0, so we would use that. This has 4 channels, so we can use any of these. The 1823 has some additional channels. So these are 6 through 2, so that's going to be these guys. Let's get 0, 0, 1, 2, yeah, these guys here. So those 4 are giving us the channel 0. Okay, now we go to bit 1. This is actually what starts and stops the reading of the analog to digital conversion process from the peripheral. So we set that to 0 to begin with. Then I'm going to just jump you down here quickly. This in the main loop, this is just turning on and off the analog to digital go. So when it's on, it'll start to read a digital. When it fills the register, then it will automatically go forward. So it's actually quite easy to work with, and a lot is happening kind of automatically on the microcontroller. And then, yeah, so, and then bit 0, yeah, so that's bit 0 is to enable. So that's happening here. This is bit 0, and then this is the go pin. So the last 2 bits are involved in getting that going. Okay. All right. So that's ADCON 0. ADCON 1, let's look at that. That's up here. So go to ADCON 1, and bit 7 is a 1, and that just means we're going to write justify. So the 6 most significant bits are going to be put into add res high. If we wanted to put just the 2 most significant bits in add res high, then we would put a 0 there. Doesn't matter too much. I can't think of too many situations where that's all that important. If you're fine with an 8-bit analog to digital, then if you do it this way, you can just read the add res high. Okay, then we have all zeros, so we're just going to use this setting for the conversion clock. So it's the oscillator divided by 2, so this will be the fastest conversion. 2 and 3 are not used, and then the last 2 bits are what is going to be our reference voltage. So we're just going to use the voltage VDD. So that means we can read values from 0 to 5 volts. Okay, so that's that. So now we're just going to clear the high and low just for initiation. Then we're going to have to do a little bit of fancy footwork here, going back and forth, because the digital output is on port 0 and the digital inputs, or the analog input, is on bank 1. So, or banks, yeah, this is on bank 0 and this is on bank 1. Okay, so this clears the register, or the pin, and then we jump into the main loop. So this just initiates the process of gathering a 10-bit analog signal. And here is where we set the bit that we're going to look at. So this is really the nuts and bolts of it right here in terms of the collecting the signal. Now the signal is there, sitting right here, and in the first 8 bits are here, and then the last 2 bits are in the low. So we're going to take bit 3. So this will be the 5th most significant bit because of the 2 in the low register. All right, so now let's look at how we're going to toggle this. So what we want this to do is, if this bit is a 1, we're going to toggle from whatever state we are in. Whether we're off, we'll toggle that to on. If we're on, we'll toggle that to off. And that will be our random telegraph signal. Then we're going to do this with a delay. So we need our delay functions that we've been using all the time. Okay, so we are going to let's call this down here, and let's see how this toggle works. So we're going to set the port to 0, or the bank to 0. It's going to read the value of RA2. So that's either on or off. If it's on, okay, this is going to skip this. So we're going to skip this. So at this point, the working register is whatever it is. So we're going to skip this down to here. Then if this is off, but it's not because we skipped it, it's going to be on. So then we're going to move in here. We're going to turn the last bit of the working register on. Then what we're going to do is read that bit. And if it is on, then we will skip. And if it was off, of course it isn't because we just skipped to here, then we're going to turn it off. So if we come in with our RA on, we're going to leave with our RA off. Now, for this to be a correct toggle, now we have to check this if we come in with our RA off. So RA2 comes in off, and we go into here. Now it's going to skip if set. So it's not set, it's off. It's going to put our working directory to 0. Then it's going to check RA2 and skip if clear, and it is clear because we came in with 0. So that's going to skip here. Then it's going to check the working registry. If this is set, it's going to skip, but it isn't set. So we're going to set RA2. And then if we hit this, our working register is 0. So we're going to, it's clear. So we're going to skip this right to the return. So we're going to return with a set. So that's working toggle now. We come in with it on, we're going to leave with it off. We come in with it off, we're going to leave with it on. And then we'll come back into our main loop. We'll delay for 20, and then this go-to will take us back up here. Note we did not, we should, in order to use the delay, we have to be on bank 0, and we are because we have, when we called the function, we got moved to bank 0 up here, and we're still there on our way here. And then when we come back up here, we get put over to our analog to digital bank. Okay, so this is what we were just seeing with the proximity detector. So let's change this now. and make this just a straight, well, let's make this a touch detector. So I'm gonna raise this up a bit to the sixth most significant bit. And I'm gonna just complete this program. And now I'm gonna undo the power, pull this over. Power it up. And now we should not see really anything because we're not reaching that threshold with the noise. And even if I get close, but if I touch, then because we are such good antennas, then we're easily swinging the voltage above the threshold. But see, notice now, as close as I get, I have to finally touch to get that to go. And notice it can pretty much, oh, there it's on, there, on. So it's basically random whether it's on or off. So this is almost like rolling a two-sided die or flipping a coin, just like that. So this would be a touch sensor. Pretty common to be off. I had this running for like an hour, and I came back to see if it had ever switched, and it never did. So even just in the house here, it never reached that threshold of voltage just by some spurious spike. I'm sure at some point it probably would catch something and flip, but at this high of a voltage to threshold, then it's just not going to. Okay, so let's switch this back now and use a lower one. So we're plugged back in. So now what I'm going to do is I'm going to take the lowest bit. So I'm going to change this to the low, and it will be bit 6. So see if we can find that here. Res low. Bit 7 and 6 are the two lowest bits. And then 5 through 0 we're not using at all. So there's our two lowest bits. So this should be the lowest of all bits. It should basically be random. So when we run this, so I will run this now, and then when we plug it in, we should just see it go all the time, because we're always going to have enough noise to be tickling that last digit, binary digit. Okay, so I'll plug this in. And now we see it oscillating. And kind of a really nice random telegraph process here. If I were to touch this, it'll go a little bit, pretty much completely random. And then, so let me show I'm going to pause and show the oscilloscope here. So there's the oscilloscope. You can kind of nicely see it flickering. Still fairly random, but a pretty nice process here. I'll touch this again, and then we'll get a much more dense switching, or rapid switching. All right. I'm going to pause this and go back. I didn't show the oscilloscope for the proximity, or for the, we did see it for the proximity tester, but for the one where I had to touch. So I'll just do that real quickly. Okay, so if you can see over here in the code, I've changed this back to the second most significant bit here, the high number 6. We can see the light is stably on here. But now I have to touch, and then we see scope, and then when I let go, it locks into either on or off, depending, just randomly. Okay. All right, so that is application of the analog to digital converter for making a random telegraph signal, and using, in this case, a proximity detector or a touch detector.